Every single time an airplane takes to the sky, it's fighting this incredible invisible battle. It's a war against forces that are constantly trying to rip it to pieces. In this explainer, we're going to pull back the curtain on the amazing physics that lets it win every single time. Okay, so let's just jump right into that question. Really think about it. How does a massive 400-ton machine stay in one piece while blasting through the air? Well, the secret lies in a field called statics. It's the science of how things stay perfectly balanced, even when they're under mind-boggling amounts of pressure. So, here's our flight plan for today. First, we'll dive into that invisible battle of forces. Then, we'll pinpoint the one spot on the plane that's most important for balance. After that, we're going to break down the 5 major stresses trying to tear it apart. And finally, we'll see what happens when things go beyond the breaking point. To really get what's going on in this invisible battle, we have to learn the language. And that language starts with one single fundamental word: force. A force is really simple when you break it down. It's just a push or a pull. That's it. Now, when that push or pull acts on something that's not moving, like a plane sitting on the tarmac, it creates an internal resistance inside the material. And we call that resistance stress. It's what's holding everything together from the inside out. But here's the thing. A force isn't just about how strong it is. It's also about which way it's going. And we show that using vectors. Think of them as arrows. The length of the arrow tells you its power, but the direction it's pointing, that's just as critical. For an aircraft engineer, getting the direction wrong is, well, it's not an option. And when you apply a force at a distance from a point, it creates this turning or twisting effect. In the world of engineering, that's called a moment. The easiest way to picture it is using a wrench. The force you put on the handle creates a moment that turns the bolt. Same idea, just on a much, much bigger scale. All right, so we've got all these different forces, vectors, and moments pushing and pulling all over the plane. So where do they all meet? It turns out there's a single, unbelievably critical point that governs the entire stability of the aircraft. And that point is the center of gravity, or CG for short. This is the absolute key. The CG is the airplane's perfect balance point. Get this. If you could somehow take a 400-ton jumbo jet and hang it from a single string attached right at its CG, it would just hang there, perfectly level. And listen, this isn't some abstract physics theory. Managing the CG is a constant, real-world, absolutely vital job. Pilots have to calculate it before every single flight, based on where passengers are sitting and how much fuel is on board. Maintenance crews have to recalculate it any time a piece of equipment is added or removed. Getting the CG wrong can make a plane completely unflyable. Okay, so now let's get to the real heart of this invisible battle. As all those forces we talked about act on the plane, they create 5 distinct types of stress. And every single part of that aircraft is meticulously designed to fight them off. All right, meet the 5 main opponents in this fight. You've got tension, compression, torsion, shear, and bending. From the tip of the nose to the end of the tail, every single part of that plane is dealing with some combination of these stresses all the time. First up is tension. This is a pulling stress. The easiest way to think about it is a game of tug-of-war. The engines are pulling the plane forward, right? But air resistance is dragging it back. That creates tension, and it literally stretches the body of the plane. The total opposite of that is compression. This is a squeezing force. It's always trying to crush or shorten a part. So if tension is pulling everything apart, compression is trying to push it all together. Then you have torsion. This is a twisting stress. The incredible rotational power of the engines creates a torque that tries to twist the entire airframe. Seriously, it's just like wringing out a wet towel. The structure has to be incredibly rigid to stop that from happening. Next up is shear. Now this one's a bit different. It's more of a slicing force. Imagine you have 2 metal plates, and they're held together by just one little rivet. As you pull those plates in opposite directions, that rivet experiences shear stress. It's a force that's trying to slice that rivet clean in half. And finally, we get to bending. Now, bending is probably the most complex because it's not really its own thing. It's a combination of tension and compression happening at the same time. And the wings are the perfect example. On the ground, gravity pulls the wings down. This puts the top of the wing in tension, stretching it, and the bottom in compression, squeezing it. But the second the plane is in the air, lift pulls the wings up, and those forces completely reverse. The top is now in compression, and the bottom is in tension. The wing has to be strong enough to handle both extremes. So, we've seen all the stresses an aircraft has to put up with, but what happens when those stresses become too much? What happens when the material just can't handle it anymore? Well, here's a fascinating fact. Anytime an object is put under stress, it physically deforms. It actually changes its shape, even if it's just by a microscopic amount. And that physical change, that distortion, has a name. It's called strain. An object under stress is always experiencing some amount of strain. And chances are you've seen this happen in real life. A perfect everyday example is a deflecting beam torque wrench. As you tighten a bolt, you're putting stress on that main metal beam. You can literally see the beam bend. That visible bending, that's the strain. And it's directly related to the amount of force you're applying, which is how the wrench lets you measure it so accurately. So why does all of this matter? Because in aircraft design, nothing, and I mean nothing, is left to chance. The next time you're on a flight, just remember that every single bolt, every beam, every panel on that plane was chosen and designed by engineers who meticulously calculated these 5 stresses. They've made sure that the aircraft can handle everything from a perfectly smooth flight to the absolute worst turbulence you can imagine. Which leaves us with this final thought. The materials we use will always change. We've gone from aluminum to advanced composites, and who knows what's next. But the fundamental forces, tension, compression, torsion, shear, and bending, they will always be there. That invisible battle never, ever ends. And winning it is going to demand the next generation of engineering breakthroughs.